All right, we are going to start our next unit today, and it's actually Unit 2, Part 2, a little extension. It's going to be very short, if you could tell, like from the thickness of the papers that you got. But we're just going to continue and extend on some of the topics that we have been in Unit 2, like multiplicities, x-intercepts, those types of things. We are going to pay much more close attention to x-intercepts because really the only characteristic we've discussed with those has been multiplicities. But we're going to go over different types of x-intercepts, meaning like positive x-intercepts, negative x-intercepts, maybe we have an x-intercept through the origin, and we're also going to explore today and tomorrow, what if we have imaginary x-intercepts? We've dealt with imaginary numbers before, right? That I, yeah, we're going to see some of that, okay? And we're going to kind of explore why we have imaginary x-intercepts today, just a little bit. So looking at the schedule ahead, since this is a very brief unit, I am aiming to get our quiz in before break. I don't think we're going to have a problem doing that. But the unit tests for this part 2 will be after break. Not the day after, okay, so not like Thanksgiving, but it's probably going to be close, meaning the day we come back would be a review day, and then the following day would be test day. Okay, so it might be fairly close when we come back. We'll see, okay, we'll see how it pans out. So, looking at our first section, we're going to take a look at something that I'm pretty sure is going to be new to all of us. It's called Descartes' rule of signs. Descartes was, I believe, a French mathematician, and he actually created the coordinate system that we use a lot in math, like the x and y plane. So you can credit him for that creation, or be mad at him, however you want to look at it, okay? Right? But we're going to take a look at how he analyzed a function, how he determined where x-intercepts were. This is like pre-calculator day, how we can analyze x-intercepts without having that technology available to us, because let's face it, we might not always have that available to us. So just as a review, we're going to go through some of these different characteristics on page 175. Can we tell, based off of the shape of this f of x graph, what we could classify it as? Like the name of the function? Yeah? Cubic, okay? And if it's a power of 3, what do we know about the x-intercepts? Do you remember our connection between the degree and the x-intercepts? Yeah? The multiplicities are supposed to add up to 3, okay? How many x-intercepts do we have on that graph? 1. What's its multiplicity? 1. So they should add up to 3, right? Where's the other 2 that we're missing? Yeah? On the what? If it was 3-dimensional, maybe on the z-axis, okay? The other 2 are what we're going to call imaginary x-intercepts. So imaginary x-intercepts are not graphable, okay? They're imaginary numbers. They're almost like placeholders, because we know that this graph should have 3, or not 3 x-intercepts, but we should have multiplicities that add up to 3, and graphically, notice how we only have 1 multiplicity, or multiplicity of 1. So the other 2 we would classify as imaginary, because we need to have 3. Does that make sense? We're going to dive into that throughout this section and unit. So what you can do is imagine if you were to kind of shift this graph up and down. Maybe you can't tell that this is cubic based off the shape. Okay, maybe you're familiar with just doing the multiplicities. But if you were to shift this graph up or down, okay, maybe something like that, notice how we would have 3 x-intercepts, all with a multiplicity of 1. Okay, but this is if we were to shift it. Okay, this isn't the actual graph. So if we were to shift it, we would have 3 zeros, all with a multiplicity of 1. So that means we could classify it as cubic. What about g of x? If we were to shift it, Can we find the most amount of x-intercepts? And that's kind of going to lead us into the type of function we have. Good, Logan? 4, quartic. Okay, so if we were to shift it down a little bit, it would probably look like that. 1, 2, 3, 4, all with a multiplicity of 1. So we could classify that as quartic. What you could do is maybe you wanted to shift it down like that. Here you would only have 3 x-intercepts, but notice how if you look at the multiplicities, it'd be 1 plus 2 plus 1, which would still lead you to quartic. So depending on how far you shift it, okay, it should still lead you to the same result. We're trying to get the highest multiplicity, because that's going to lead us to the type of function. Bless you. All right, so far so good. Let's take a look at these x-intercepts a little bit further. So if we were to pay attention to the f of x graph, we want to list how many positive x-intercepts we have, how many negative, how many are 0, meaning at the origin, and then how many are imaginary. We're eventually going to get to the point where we can create this table without actually looking at a graph. Okay, we're going to try to do this by hand, but that's going to be in the future. Looking at this graph, how many positive x-intercepts do we have? Do we have any x-intercepts with positive values? No, so we'll just write 0. Do we have any x-intercepts with negative values? How many? Just 1, right there. Do we have any x-intercepts at the origin? No, so we'll write 0. All right, so kind of like how we already discussed, we know that f of x is cubic, so we know we should have 3. We only have 1, so that means the other 2 must be imaginary. All right, if we take a look at g of x, we have 1 positive x-intercept. We have 1 negative x-intercept. We don't have any x-intercept at the origin. What about imaginary? 2, right? Because they have to add up to 4. 1, 1, 2 would give us 4. All right. We doing okay so far? Good. All right. The rest of it's kind of throwback review, so we'll see how we do with this. Can we state some end behavior? Maybe we'll use rise and fall as our classifications. What about f of x? Can we describe what the ends are doing? Good, Caitlin? There we go. Fall on the left, rise on the right. What about g of x? You keep going, Caitlin? Yeah. Fall, fall. Hopefully that makes sense because we said f of x was cubic. Notice how that's an odd degree, so you should have opposite end behavior. And quartic is an even degree, so they should be the same. Checks out. What about if we had the equation of these different graphs? Would the leading coefficient be positive or negative? What do you think, Julia? How'd you know? Those are good. There we go. So you got to look at the right-hand side. If the right-hand side rises, we're positive. Fall, we're negative. Perfect. All right. What about, can we look at the graphs and identify some factors that the equation would have? Factors meaning like the little parenthesis set or parenthesis pair. Good, Hadley? Where'd that come from? That's perfect. All right, we have an x-intercept, so we can convert that x-intercept to a factor, which would be in the equation. What about g of x? Good, Caitlin? There we go. All right, so looking at the x-intercepts, -3, +3, we can produce the related factors. Good. All right, and last but not least, what about domain and range? How far left, right, low to high can these graphs go? Let's look at f of x first. If you were to drag your pencil, do you have to skip over anything? Any ideas for the domain or range? F of x? Yeah? For the domain? Okay. And then the range? Same thing. Good. All right. Forever left, forever right, forever down, forever out. No holes, no jumps, no asymptotes. We're good to go. What about g of x? Good, Leanie? Okay. And then can you try the range? 5, okay. Can we touch 5? Yep, so we'll do our bracket. So notice how 5 is your absolute maximum, the highest height that the graph has. So we'll stop there. All right, I think that's a good review. So this is leading us, at least this chart section, I guess, is leading us into Descartes' rule of signs. What we're going to try to do is just look at an equation, okay, no graph. We're just going to look at an equation and try to determine how many x-intercepts do we have on the right-hand side, how many do we have on the left, and how many are at the origin. Okay, so we're going to just take a look at an equation. We're going to write down the rule, I guess, or how we determine this. I'm already anticipating it to do this. Go right over our heads, all right? But we're going to go through some examples. Okay, maybe it won't go over your head, which would be great, but it's new to us, so it might. What we're already familiar with, though, and maybe you didn't know it's called this, is the fundamental theorem of algebra. Okay, basically related to the x-intercepts of a graph. So the roots, or zeros, or x-intercepts, whatever word you want to use, can be one of 4 possibilities. You can have positive x-intercepts, you can have negative x-intercepts, you can have x-intercepts that are 0, meaning at the origin, or they can be imaginary. Bless you. This is going to be our main focus of this section. We're going to try to figure out where all the x-intercepts are located and if we have any imaginary ones. All right, so I'm going to write down Descartes' rule of signs. You just copy it down and then we're going to look at it a little bit further. So Descartes' rule of signs tells us that the maximum number of positive x-intercepts or roots is the number of sign changes in the f of x function. Okay, the original function you start with. Very similarly, the max number of negative x-intercepts is the number of sign changes in f of negative x. Okay, a different function. Gary, did you already take it once?
Yeah.
Yeah.
Can I get a pass? Because I have to get into the library.
So you're going to go to the library and then come back?
Yeah.
Yeah.
Thanks.
Yep. Was I right? Did it do this? Yeah. It did like a circle and then it went back, right? Gone. Okay. So we're basically going to look at the equation itself. We're going to look for sign changes, like positive to negative, negative to positive, and however many of those we can identify, that's the maximum number of x-intercepts, either positive ones or negative ones, that the graph would have. Okay, the max number. You could have less, okay, but that's the maximum number. One thing, though, that we have to pay close attention to, or at least practice, is developing this f of negative x equation. Because f of x is just the equation they give you, the one that you start with. This one you are going to have to figure out. So that's what we're going to practice for this one here. Okay, we're going to say p of x is this original equation. We want to try to figure out if we were to plug in negative x for all of those x's, how would that change the terms? Can we think about it? If you were to plug in a negative x and then raise it to the fourth, what would happen? Yeah? It would be positive, meaning this term is going to stay the same. Okay, positive means it's just going to stay the way it is. What if you were to plug a negative x into an x to the third? Yeah. It's going to be, say it again? Negative, because you have an odd number of negatives. Okay. All right, so if this term is negative, that means we need the opposite, bless you, of that term. So instead of being positive x to the third, we're going to write negative x to the third. Okay, we're going to repeat the process for every single x. Now, can you start to see a pattern, maybe? What terms are going to switch? Good, Logan? The odd terms, so the odd powered terms. So this one's going to switch and this one's going to switch because it's a power of 1. So the minus 8x squared will stay the same. The next term can change to a negative 2x. What about the plus 3 on the end? Is that going to change? Why not? There's no x there for it to change. It's a constant. Okay, it's going to stay a plus 3 forever. Okay, so this is what we're going to have to think about or develop in order to get this new equation. Basically, whenever you have an odd power term, you're just going to switch the sign. Okay, that's all really we have to look for. So this is going to lead us into how we can find the maximum number of positive x-intercepts and negative x-intercepts. Let's take a look at the original p of x, the one at the top. I'll go ahead and write this a little bit bigger. So when you look at the original equation and you read it from left to right, we want to see how many sign changes there are. Can we identify where we change from a positive term to a negative term? Or vice versa? Let's see. 2x to the fourth, positive. X to the third, positive. Negative 8x squared, negative. So this one was positive, this one was negative. There's a sign change. If we do, or if we start again at negative 8x squared, and then we go to a 2x, that's a negative to a positive, that's another sign change. And then we go from 2x to 3. Both of those are positive. So when we look at the original equation for those sign changes, it looks like we only have 2. We're going to do the same thing, but now for this new equation that we developed when we were thinking about plugging in negative x. Alright, so I'm just going to rewrite the one that we had up here. Alright, let's look for sign changes. Positive 2x to the fourth minus 3x squared. there's a sign change. Then we have a negative, which is not a sign change, another negative, not a sign change, but then a positive 3. So there's another sign change. So we have 2 sign changes there. So what Descartes' rule of signs is telling us is for this graph, okay, of the original equation, whatever it would look like, we have at most 2 positive x-intercepts. We could have less, but we could also have at most 2 negative x-intercepts or less. So we have at most 2 over here and 2 over here. Okay, nothing in the middle, nothing at the origin. So if these are the possibilities, okay, that you could have, we also need to think about, well, what if we have less? Okay, what are the other possibilities? Can we have 1? Can we have 0? Okay, and that's when I want you to take the time to read this little paragraph. So Descartes' rule of signs gives you the max. How can you figure out the other options? Did we read it? All right, let's check this out. So for this function, okay, the same one we've been doing since the top here, okay, p of x, how many positive roots are possible? Descartes' rule of signs gave us a maximum of 2. But what's another possibility? 0. Okay, you could go any multiple of 2 less than the maximum. So what if, for instance, Descartes' rule of signs gave us 6 as a max? What are the other choices? Yeah? 4, 2, 0. Okay, what if Descartes' rule of signs gave us 3? 2 less would be 1. 2 less would be negative, so we can't do that. Remember, these are the number of x-intercepts, so you can't have a negative number of something. Okay, so we can always go 2 less, never negative, okay, but we're going to stop at 0 if that's a possibility. So for the negative options, that came from the p of negative x equation, Descartes said that we have at most 2. So if we subtract 2 from that, another possibility would be 0. Okay, so Descartes gives you the max. You can subtract 2 as many times as you need to figure out the other possibilities. All right, so Descartes' rule of signs gives us a way to determine positive x-intercepts and negative x-intercepts. Let's go ahead and take a look at where we might have an x-intercept at the origin, okay, aka a 0 x-intercept. So we're going to take a look at 3 examples here as well as their graphs to kind of make all this click for us. In the boxes, we're going to rewrite everything in factored form. So maybe we'll just start with f of x in its entirety and we'll go through the other ones. How do you want to try to factor f of x? What do you think, Logan? Take out an x. All right, we're left with x squared plus x minus 2. Can we keep going? Good, Lainey? I like it. So we kind of have that I am setup that we can go through from there. All right, so if those are the factors, we should be able to identify the x-intercepts. We'd have 0, -2, and 1. And graphically, 0, -2, and 1 check out. So if we were to take a look at the factors, okay, the ones that we just developed, how many times is x equals 0 a root? If you were to just take a look at your factors up here, how many times is 0 an x-intercept? Meaning, what's its multiplicity? How many times? Yeah? 1. How'd you know 1? Okay, graphically, yeah. But if you were to just take a look at these factors, how would you know it's 1? It's a power of 1. Perfect. Okay, so we'll say 1 time because x was a GCF once. Okay, you could only pull out 1x. And graphically it makes sense because we go straight through. Okay, but again, we're trying to look at the equation. The graph is a good checker. Okay, but we're going to try to just look at the equation. Let's try g of x. Can we factor it? Go ahead, Caitlin. Take out x squared. We're left with x minus 3. X-intercepts would be 0 and 3. Graphically, they check out. In this example, how many times is x equals 0 a factor? Yeah. 2. How'd you know? All right, because x was a GCF twice. Okay, you were able to pull out 2 x's in this case. And graphically it makes sense because notice how we're bouncing at the origin. Okay, that multiplicity of 2. How do you want to factor the third one? Grouping, we have 4 terms. All right, so out of the first group, we'll take out an x squared. We're left with x plus 1. What can we take out of the second group so that we're still left with an x plus 1? Bless you. Negative 4. All right, so grouping x squared minus 4, x plus 1. Can we keep going? Yeah. Difference of squares, we'll have x plus 2, x minus 2, and then an x plus 1. So x-intercepts, negative 2, positive 2, negative 1. Graphically, they check out. How many times was x equals 0 a factor or a root? Never. We'll say 0 because x was not a GCF. Okay, if you look at your ending factors, notice how we don't have a single x out front like we did in the previous 2. So if you don't have a GCF of x, notice how you'll never ever go through the origin. Okay, that's what's creating that x-intercept at that spot. So how can we just look at the equation to help us determine if we have an x-intercept at the origin? Can we look at the 3 examples here? Why did these 2 have an x-intercept at the origin and this one didn't? What made it special? Yeah. These 2 do not have a constant term. Notice how this one has a constant of negative 4, which graphically should be your y-intercept. So if you have a y-intercept at negative 4, that obviously means you don't have a y-intercept at 0. Okay, so we'll say f of x and g of x are missing a constant term. So if you have a constant term, that's where your y-intercept is. And if it's anything other than 0, there's no way you're going through the origin. Are we doing okay so far? Do we see it? Okay. Based on what we've done, how will you determine the number of times x equals 0 is a root? How can you just look at the equation to determine if it's 1 time, 2 times, nothing? What do we think? Yeah?
Just depending on how many numbers you're working with.
like if there was like a plus x on the end, you're saying, okay. So in this case, you were able to take out 2 x's, whereas this one you were just able to take out 1, okay? So I like that. We'll say, how will you determine? We can say, how many times x is a GCF? Okay, how many x's can you take out? That depends if you go through the origin, if you bounce at the origin, if you're level at the origin. That's telling you your multiplicity. Okay, how many times you can take that x out. So let's just take a look at a quick example here at the bottom. This is the same p of x equation that we did the Descartes rule of signs for. So we already know the possible positive and negative x-intercepts for this equation. Now let's try to determine how many x-intercepts we have at the origin. What do we think? How many times is x a GCF? Yeah? There's a constant term. All right, so we'll say no x-intercept at the origin because there is a constant term. All right, so let's think about this. We've already gone through the options for positive x-intercepts, negative x-intercepts, and now we know for sure there's nothing at the origin, okay, for this p of x equation. How many x-intercepts should we have? 4, right? Now, if you take a look, where'd it go? On the previous page, we said there were at most 2 positive ones, at most 2 negative ones. What if we don't have any positive ones? What if we don't have any negative ones? And we know for sure we don't have any at the origin. But we need to have 4. All 4 are imaginary, okay? We're going to get into imaginary ones tomorrow. We're going to end there for today.